Hey everyone, welcome back to the channel. In today's video, we are diving into inter-process communication, or IPC, a fundamental topic in operating systems. If you have ever wondered how processes running on your system can share information and work together, IPC is the answer. So let's break down how IPC works, why it's essential, and the different techniques operating systems use to enable this kind of collaboration. To start, let's define IPC. Inter-process communication is a set of techniques that allows processes to communicate with each other, sharing data, coordinating actions, or notifying each other about events. Since each process has its own memory space, they can't directly access each other's data. IPC provides a bridge for sharing information, ensuring processes can cooperate without causing data conflicts or security issues. IPC is crucial for multitasking environments. When you use multiple applications at once, like streaming music while browsing the web, these processes need to exchange data or resources, often without you even realizing it. IPC is foundational for building complex applications. Imagine a web browser handling requests from multiple users simultaneously. Each request might be managed by a separate process, and they need to share information about resources like database connections, cache, and session data. IPC enables this kind of collaboration, making systems faster, more efficient, and capable of handling concurrent tasks. IPC also improves resource sharing, allows for modular design, and is critical in distributed systems where different parts of an application may run on separate servers. Operating systems offer a variety of IPC methods, each suited to different situations. Let's go over some of the most common IPC mechanisms. Number 1. Pipes. Pipes are one of the simplest forms of IPC. They allow data to flow in a one-way or two-way channel between two processes. In Unix-based systems, pipes are often used to connect commands, sending the output of one command as an input to another. There are two main types, anonymous pipes and named pipes. Anonymous pipes only allow communication between processes with a common ancestor, like a parent and a child. Named pipes can be used by unrelated processes, making them a more flexible choice. Number 2. Message queues. Message queues allow processes to exchange discrete messages with each other. Each message is stored in a queue where processes can read or write messages. This method is great for scenarios where processes need to communicate in a structured way. In message queues, messages are sent to a queue identified by a unique key. Processes can then retrieve messages from this queue when needed. Message queues ensure reliable, ordered communication, making them ideal for tasks that need to be completed in a specific sequence. Number 3. Shared memory. Shared memory is one of the fastest IPC methods because it allows multiple processes to access a common memory space directly. Instead of passing messages back and forth, processes can read from and write to a shared area in memory. To avoid conflicts, processes use synchronization techniques like semaphores or mutexes to manage access to shared memory. This approach is frequently used in applications where high-speed data transfer is essential, such as in real-time systems. Number 4. Sockets. Sockets are more commonly associated with network communication, but they are also a powerful IPC tool. They enable processes to communicate over a network or even locally on the same machine. Sockets provide a two-way communication link, allowing data to be sent and received. They are widely used in client-server applications and are the foundation of networking, as they enable processes on different systems to communicate as if they were on the same machine. Number 5. Signals. Signals are a form of IPC used primarily for sending simple notifications from one process to another. When a process receives a signal, it takes some action, such as terminating, pausing, or running a specific handler function. Signals are lightweight and useful for simple notifications, but they are limited in the type of information they can carry. Because of this, they are typically used for signaling events rather than exchanging large data. One important aspect of IPC is synchronization. When multiple processes access shared resources, they can run into problems like race conditions and deadlock. Synchronization techniques such as locks, semaphores, and mutexes help manage access to shared resources, ensuring that processes don't overwrite each other's data or become stuck waiting for a resource. For example, in shared memory systems, if two processes try to update the same variable simultaneously, the result could be unpredictable. Synchronization tools ensure that only one process can access a critical section of code or data at a time, maintaining data consistency and program stability. Now that we understand the basics, let's look at some real-world applications of IPC. Number 1, web servers. In a web server, IPC enables multiple worker processes to handle incoming requests and share access to resources like databases or caches. Number 2, operating system kernels. Operating system kernels rely on IPC to manage processes, handle interrupts, and communicate with hardware. Number 3, embedded systems. In embedded systems such as those in cars or medical devices, IPC allows different modules to communicate and work together in real time. Number 4, multiplayer games. In multiplayer games, IPC is crucial for synchronizing player actions and maintaining a consistent game state across different devices or servers. Understanding IPC is essential for developers working in multitasking or distributed environments. Knowing when to use pipes, message queues, shared memory, or sockets allows you to build efficient, reliable, and scalable applications. It also opens doors to advanced topics like distributed systems, where IPC principles are foundational for connecting processes on different machines. So, just a quick overview of IPC, covering the basics of inter-process communication, different types of IPC mechanisms, and their real-world applications. Whether you are building complex applications or optimizing system performance, IPC is a key skill that can make a big difference in your development journey. If you found this video helpful, don't forget to like, subscribe, and hit the notification bell so you don't miss any future videos. Thanks for watching, and I will see you in the next one, inshallah. Assalamu alaikum.